Hi, everyone. Just starting up the broadcast now for our webinar. We're just going to wait a couple minutes here to see if anyone else is going to be coming in, and then we'll start up. Thanks. All right, so we'll start up here. I'd like to thank everyone for joining us for the webinar today. We have a good lineup. We've got Dr. Stephanie Taylor speaking, Mike Schofield speaking, and then myself speaking at the end, and we'll be going through our agenda shortly here. I'd like to bring up a couple major events coming up. So the ASHRAE AHR event from January 14th to 16th. Nortec will be attending. We'll be at booth B3821, and we're inviting you to join us there in Atlanta this year. So we've got some big announcements to make this year, and we're excited for the show. So without further ado, we'll start up. Today's webinar is titled Make Sure to Water Your Humans, sponsored by Nortec, part of the Condair Group. Today's presentation summary, we'll start off with Dr. Stephanie Taylor talking about why humidify for health, followed by Mike Schofield. He'll be talking about how to humidify and save energy using a VAV fan system. And then I'll finish off today's webinar talking about low energy and high hygiene products, touching on ASHRAE Standard 170 and our Nortec DL system. With that, I'd like to pass it over to Dr. Taylor. Stephanie, are you ready?
I'm ready, thanks.
Okay, and I'll just pass you over control here. Sorry.
So thank you for everyone who's on this webinar. So we are titling this, Make Sure to Water Your Human. Sometimes we forget about this aspect of the indoor environment. We tend to humidify for wood and for materials, for data servers, but we need to take a look at human health. Why do we need to take a look at human health? Graham?
Yep, there you go.
Okay. So given the exorbitant costs of healthcare in the U.S. and actually worldwide, for many countries anyway, something's going wrong. For example, patients go into the hospital and die from going into the hospital. In fact, entering the hospital as a patient is the third leading cause of death in the U.S. That is just really, really frightening. Healthcare costs are out of sight. Those two things might be linked. In addition to the dangers of a hospital, more and more people have autoimmune and chronic inflammatory diseases, autoimmune disorders such as lupus, systemic lupus, Lou Gehrig disease, which is amyotrophic lateral sclerosis, chronic inflammatory diseases such as inflammatory bowel disease, and other things. In addition, new infectious diseases are emerging, and ones that we thought were off the globe are coming back, sometimes with vengeance. So we need to ask, what in the heck is going on? So just for example, I hope nobody who's listening actually got the flu last year, but it was one of the worst seasons that the CDC's ever seen. If you look at the red line, you can see that was as of January 2017, but the incidence of people with the A1 influenza had exceeded the previous years. Baby boomers were hit the hardest. However, pediatric mortality was the highest. And it's not just infectious diseases. These chronic diseases, stroke, heart attacks, cardiovascular disease in general, diabetes, high blood pressure, arthritis, high cholesterol. The projected increase in population with these problems is on the rise. So that is just mysterious. So we need to ask, what's going on? Well, one thing that's going on for human beings is that we're indoors almost 90% of the time. The indoor environment has changed from how it was several centuries ago. We now have tight building envelopes, highly ventilated systems, and the indoor and the outdoor air characteristics are often vastly different. So why does that matter? Are we thinking about health when we design buildings? Because given the increase in problems and the amount of time we spend indoors, it behooves us to ask, is there a link? And when we think about designing and operating a building, what are building professionals considering? Well, it comes down to money. Whether that's good or bad, that seems to be the case. So we think about construction costs, energy consumption, we think about protecting building materials and indoor goods, and we think about occupant comfort. But from this list, there's something missing, and that something is occupant health, not just comfort. So let's take a more detailed look at the indoor environment, because we now know, and this is a very exciting time to be considering health in the indoor environment, because thanks to new tools, Graham, can you get that going?
Sorry, Stephanie, I couldn't get it managed here.
Okay, well, I think Graham's office isn't humidified properly. But anyway, that's a joke. We now know, thanks to new DNA analysis tools that actually give us a more detailed view of what's indoors with us compared to tissue culture techniques, we now know that we're surrounded by microbes. And as I'm talking here in my office, I'm emitting little droplets, about 100 microns in diameter, that contain all the viruses and bacteria that are in my mouth, in my upper respiratory system, digestive system. And the same for everyone who's listening to this. Hopefully you're all breathing. And as you breathe, droplets are coming out of your mouth, carrying the organisms that you have. Skin particles are shedding into the air. So we have a very active exchange between our bodies and the indoor environment. Let's see if I can go to the next slide. So since we've been using DNA and RNA analysis tools, we now know that each of us, human beings, is only about 30% by cell number, 30% human. The other 70% of our the cell number are microbial. So this is actually startling for many people. And furthermore, it's not too much of a leap of imagination to realize that the organisms that are coming out of us and off of us are going into the built environment. And people who are in these spaces that we're in now, this morning or yesterday, the day before, they left their microbial signature in the spaces as well. And studies at the University of Oregon have shown that the whole community of microbes in a building, known as the building microbiome, those communities are determined by how we use spaces and how they're ventilated. So that's interesting. And when you think about evolution, you think about organisms respond to their environment. We need to ask, are we designing and managing buildings to foster communities of good microbes or of pathogens, the ones that cause disease? So if we want to say, okay, we need a new building, we need new building parameters to determine whether we're operating our indoor environment correctly. So where can we get that data? So a great place to get data on people in buildings is actually a hospital. So and now I'm going to tell you briefly about a study which was done to do exactly what I just said, to take human health data and reflect it back on the built environment to see if diseases were indicative of any particular building parameters. So this study was done in a brand new hospital, opened up in the beginning of 2014. It was LEED Silver, state-of-the-art, 300-bed hospital, all private rooms with vestibules. So 10 rooms were taken in this hospital, 5 on one floor and 5 on the floor above. The rooms were med surg and oncology, so there was no pediatric. There were no pediatric patients, no OBGYN, no psych patients. So over the course of a little more than a year, all of these patient room parameters were monitored. So carbon dioxide, lighting levels, temperature, staff and visitor hand cleaning were monitored, room air changes, room traffic, indoor and outdoor relative humidity, absolute humidity, outdoor air fractions, and room pressurization. So from the room, we had about 8 million data points. We took all of those points and reflected them back to patient outcomes in those rooms. So over that year, we had almost 300 patient outcomes to consider. And in this webinar, I'm going to talk to you about new infections that patients got from being in the hospital, now known as healthcare-associated infections. We used to call them nosocomial infections. So again, we're looking at patient room parameters and seeing if any of them are related to the incidence of new infections. So what we found, and this was startling to us, it was not at all what we expected. We found that looking along the x-axis here, we start in the winter time, go through the summer and back to the winter. And on the y-axis, we have relative humidity. And you can see as the relative humidity went just from around 32% up towards 42%. So the relative humidity is the blue line, average room in all 10 rooms. As the relative humidity went up to 40 and slightly over 40, the incidence of new infections plummeted. So we thought, okay, well, there's a confounding variable that our statistician did not isolate. Maybe it's flu season. Maybe there are just more visitors in the winter. People are more careless with hand hygiene. Maybe there are other factors. And the statistician explained again and again and again that this was an independent variable. So this doesn't show causation, but it shows a statistically significant correlation between dry air in the patient room, meaning relative humidity. As you can see, the lower it goes, the higher the infections. It shows a correlation between patient room relative humidity and patient infections. So we were still skeptical, so we did another study in a long-term care facility looking at the same parameters. And as you can see, again, on the x-axis, we have relative humidity. On the y-axis, the average number of infections. And the blue line shows that gastrointestinal norovirus, notavirus, and C. diff, the incidence of those infections was related to the indoor relative humidity. So at 10%, you can see both the GI and the respiratory infections were high, and the incidence comes down between 40 and 60%. You have a nadir of these infections. So something about that 40 to 60% range was very, very protective for the patients. Again, that's a correlation. This study done by Dr. Reisman in the Mayo Clinic was actually shows causation. So here, this is looking at preschool influenza A attendance. So half of the school was humidified to 45%. The other half was just left to do what it does in the wintertime. So it averaged around 20%. And this study looked at the percentage of the airborne particles that were infectious, that were influenza A. So you can see when the humidity is low, 49% of the particles were infectious versus 19% in the humidified space. And not only were there more infectious particles, but the actual virulence of the particles was higher at the dry, in the dry classrooms. And that translated to children being absent from school. So 22 children missed school because of influenza A in the non-humidified spaces versus 9 children in the humidified classrooms. So this is a great study. Dr. Reisman is going to talk about this at the ASHRAE National Convention in January, because this shows an intervention that then turned things around. So what is it about dry air? Well, for one thing, pathogens, or the bad microbes, the ones that cause pathology, they actually love dry air. And this is new information to us. We didn't know this before we used metagenomic techniques, or at least we didn't see it as clearly. We thought that the particles floating around in the air were dead because tissue culture techniques didn't reveal that they were actually still alive and infectious. But we now know that pathogens, or the bad microbes, they travel for great distances and a long time when the air is dry. They hunker down into a spore form, and they have increased survival and infectivity. They get access to our deeper tissues, such as more deeply into our lungs, and they are able to evade surface cleaning. We live in a three-dimensional world, so particles that are on a table or on a horizontal surface will become resuspended if the air is dry and there's air movement. For example, just to show you this a little bit more visually, in dry air, the 100-micron diameter particles coming out of my mouth as I'm speaking right now, those droplets will shrink to create equilibrium with the air. So at 20% relative humidity, fairly quickly that droplet will shrink down to 0.5 microns in diameter and become what is known as a droplet nuclei. And those droplet nuclei have been recovered not just 21 days later, but years later. And they're still infectious. So when they land in a new host, the next person, they can cause an infection. They're not dead. And this is fascinating. This study shows that the influenza A virus, this was done in guinea pigs, is more infectious, not just more of them, but the influenza A virus is more infectious when the air is dry. So you look at the y-axis showing viability or infectivity, and you can see when the relative humidity is low on the left side of this graph, the infectivity is high. And then moving along the x-axis at 40%, the infectivity comes plummeting down. We don't really know for sure why that happens. With many viruses, the infectivity will go up again at 6. Not many. Some viruses, the infectivity rises at 60%. And this same pattern is true for many gram-positive and gram-negative bacteria as well. So again, we have some theories about what happens inside of a droplet to make this change in infectivity occur, but we're still trying to figure it out. And this research just came out in July of 2018. So here on the left, you have some bacteria that are alive. You can see some movement. You can't really tell if those are what the vibrations are caused by, but those bacteria are alive. And then in July, this group perfected the immunofluorescent staining, and you can see on the right side, the bacteria, which can be airborne, have projected this pilus out and are scavenging the red particles, which are DNA particles from any fragmented bacteria that are in the environment or in the air. So if that bacteria that's sticking the little hair out can use whatever genetic material is in the red fragment, it will. I sort of think of it as a bottomless ATM machine. So, for example, if there are antibiotic-resistant genes in those red fragments, the bacteria will absorb those and have acquired antibiotic resistance directly, without any mutation, without any reproduction. So the scientists said this antibiotic resistance can spread through the air, and yes, you should be terrified. Well, I don't want you to be terrified, but I think we need to take the problems that are associated with dry indoor air very seriously. So we know these things. This data has been out. Actually, there's quite a bit of research done before 1985, and now again research is coming out with these new techniques. And yet, our indoor environment, especially in the winter, is as dry as the Sahara Desert. So, is that a good thing for human beings? No, it's not. And if we had more time, I could take you through all the different physiological systems, but we just need to save time for some of the solutions to this problem. But we need to realize that humidification, that means indoor air hydration between 40 and 60% relative humidity, is needed to limit airborne transmission of diseases, to decrease the burden of allergens in the air. You know how if you have hay fever, it rains and you feel better. That's because the particles have been removed from the airborne environment. Indoor air hydration is needed to hasten wound healing, and just for general sense of well-being. Our organs stay hydrated. We have easier breathing, less reactivity to our airways, less skin itching. Our eyes don't get red and irritated. And actually, we now know that people sleep better when the air is humidified. So here we now have a push-pull situation. Building professionals are still in the mindset, unless you've got a data server or wood or fruit or some material that you need humidification for, building professionals think about keeping the building dry. Now that we know that human occupants need humidification, us clinicians are saying, wait a second, we can't manage our indoor environment like that. So what are we going to do? So at this point, I just want to point out that when there's a positive return on investment from humidification, it is in place. So, for example, if you're a research animal at the NIH facility where there's a clear cost on your head, you're going to be in 40 to 60% relative humidity. Or if you're an astronaut who has a lot of money invested in their training, the spacecraft up in space where there's no moisture is also humidified. So is there a business model? So actually there is. This hospital where we did the study lost $15 million in 1 year off of the 6 most common healthcare associated infections. And that money is no longer reimbursable. So that's a big hit for that hospital. And they tied up a lot of patient bed days with non-reimbursable care. So there is a business model. So now we need to start thinking about strategies to solve this. So I'm now turning this over to Mike Schofield.
First slide, Graham. Today, I would like to introduce a variable air volume design using overhead air delivery systems that will reduce fan energy cost, reduce humidification costs, reduce artificially high air change rates, improve indoor air quality by controlling room relative humidity. We'll analyze 22 northern U.S. cities based on their bin weather data. These are cities up near the Canadian border to show the annual humidification benefit of this design. Next slide. Okay, this shows the
Hold on, Mike. I think you're muted there.
there
you go.
I'm back on.
Yep.
Oh. This is a schematic of the variable air volume design that we want to discuss. In the heart of the design is a air-to-air heat exchanger known as a heat wheel. And this device recovers the heat generated by people, lights, plug load inside our little furnace known as an office building, transfers it into the makeup air side to the building, where it preheats 100% outdoor air. The other component that we're going to dwell on here is the adiabatic cooling humidifier shown here. This device is a 12-inch deep rigid media pad selected at full VAV fan flow at 400 feet per minute face velocity. And when we turn the fans down to 50% flow, as we do during the winter, during the flu season, the adiabatic saturation efficiency jumps up to 95 to 98%. Likewise, the heat wheel, which is selected for 75% sensible effectiveness at full flow, it increases up to an 83% effectiveness at the VAV wintertime turn down to 50% flow. The dampers A and B are used to mix preheated outdoor air with unheated outdoor air so that we deliver to the adiabatic cooler humidifier a wet bulb that allows us to furnish a 40-degree dew point delivery into the building. Now, let's take a minute and talk about something that the northern climate people are well familiar with, and that's the morning warm-up cycle. Every building after night and weekend shutdown pretty much goes into a cycle where all of the outside air dampers, A, B, and C, are closed, the heat wheel is off, the exhaust fan is off, and damper D is open, bringing return air from the building through the hot water coil where it is heated, because the building during nighttime and weekend is allowed to drift down to 60-degree dry bulb. So we preheat the building so the temperature is comfortable when the office workers or classroom students come to occupy the building. What I'm going to suggest is that in addition to preheating the air, why not pre-humidify the building? Because due to moisture migration from the building during nighttime and weekend shutdown, the moisture migrates out of the building and indoor relative humidities are allowed to drop down to 20% or below. So by preheating and humidifying this air, we not only have a comfortable temperature to greet the employees or the students, but we also have a relative humidity that is up in the comfort zone described by Dr. Taylor and others, 40 to 60%. There was a very interesting article last year in the ASHRAE journal. Perhaps some of you read it. Described the mechanism by which water vapor molecules are stored in buildings. It was written by Joe Listerberg, and it was in the September 2017 issue entitled "It's All Relative." What Joe describes is quite fascinating. It turns out water molecules are stored inside buildings in the vapor state, and they are stored on hygroscopic materials inside the building. When the relative humidity indoors drops, then these molecules of water are released to the atmosphere and rehydrate the indoor air, allowing us to hold a much more stable indoor relative humidity during the occupied hours. So basically, this pre-humidification, preheat strategy that I'm describing would allow us to replenish the water vapor molecules that escape during night and weekend shutdown by migrating outside the building. Next slide. All right, this is the psychometric chart that shows the process for the wintertime operation of this heat recovery and humidification design idea. Bin zone 1 at the extreme left is the extreme cold ambient conditions when we have to operate the preheat coil to get us up to an adequate wet bulb that'll allow us to hydrate the building to a 40 dew point. Let's look at the green area, zone 2. At 20 degrees ambient dry bulb, we have enough heat available in the building to preheat through heat recovery the outdoor air horizontally, as shown here, along the line until it intersects the wet bulb of 40 degrees at the adiabatic cooler humidifier, and then it moves diagonally up to saturation, where when we're close to saturation, the dry bulb is the wet bulb is the dew point. So all three temperatures are within 1 degree of one another, so we can accurately measure dry bulb. But for years, commercial grade thermostats or temperature sensors have not been able to accurately and repeatably measure wet bulb or dew point. But by having a high saturation efficiency device, as we have in this case, we are sure that if we're delivering a 40-degree dry bulb to the space, we are in fact within a degree of 40-degree dew point. Look at the hydration of the outdoor air from 20-degree dew point up to 40-degree dew point, which allows us to hit our target during the driest conditions of the year and maintain the minimum 40% relative humidity during daytime occupancy that Dr. Taylor and others are pointing out result in a much healthier indoor environment. The last zone, bin zone 3, is enclosed by the wet bulb at 55 degrees on the top side and the wet bulb of 40 degrees on the bottom side. And in this zone of operation, not only do we get better hydration, we allow the dry bulb to float up from 40 to 55, but not only are we hydrating the air, but the fresh air being introduced to the space is well above the minimum dictated by our ASHRAE ventilation standard 62.1. Well above the 15 CFM per person is being introduced in this area. And the best part about it is this is an area of zone 3 where refrigeration typically is required, certainly above 55-degree dry bulb, to deliver the 55-degree dry bulb or lower to the space. But since we've shunted the heat wheel and its parasitic loss out of the system during this point of operation, the EER, the cooling EERs, approach 100. Compare that to a refrigeration cooling EER of 15 to 20. It's about as close as you get to free cooling as you're going to get, in addition to the hydration we're providing. Let's talk a minute about the room target, 70 to 75 degrees, and basically 40 to 60% relative humidity. Since VAV is a cooling-only system, the VAV terminal provides the CFM flow to satisfy the room thermostat set point. Because our design uses 100% outdoor air, the core zone boxes in the center of the building may be set at minimum CFM flow to meet either the ASHRAE Standard 62.1 ventilation requirement or the room cooling load. The delivery of a minimum 40-degree F dew point to the zone ensures that the minimum 40% room relative humidity may be maintained. The next thing I'd like you to consider is that why do we use 40 degrees as a delivery during the coldest months of the year? It seems counterintuitive. But the fact is, by using this low temperature, it does allow our VAV box to turn down, which saves fan energy, but more importantly, it reduces air change rates. It's been shown that room air turbulence in the human breathing zone can actually spread further from the host airborne pathogens such as the flu virus and further from the host um, within the human breathing zone indoors. There was a research project by ASHRAE RP 1515 recently completed that concluded that VAV terminal boxes could be turned down to 10% flow without losing CFM flow control or dumping. In the buildings tested, overcooling complaints actually declined when the VAV boxes were set at lower minimum flows. Next slide. Okay, this is the conclusion of my talk, and it summarizes the 22 cities on the northern border of the United States that we looked at. And in the bin zone 1, on an average of all 22 cities, only 9% of the annual hours reside in bin zone 1. Now, remember, this is based on a 24/7, 365 duty cycle. So if this was a daytime only building operation, many of the zone 1 hours measured here or shown here would move into zone 2. And I also suspect that due to global warming, many of the hours in bin zone 1 have actually shifted into bin zone 2. Bin zone 2 is where we use the air-to-air heat exchanger to provide the heat, which we extract from the building exhaust air to deliver our 40 dew point to the building and hydrate the building without humidification costs. And we see that an average of 50.7% for the 22 buildings reside in zone 2. The bin zone 3 is the one where we can shut down mechanical cooling, bypass the heat wheel to shunt its parasitic loss out of the system, and provide hydration and free or EER, high EER cooling with the refrigeration off in these hours. Now, we listed the elevation on the left side there because it appears, if you study the results we found here, that as you move closer to the west coast and as you go up in elevation, the number of hours in zone 3 increase. As an example, if you look at Washington, Seattle, Washington, there are 48.2% of the annual hours in Washington due to its mild winter climate that reside in bin zone 3, where we can get low cost cooling and hydration using warmer ambient conditions. So the fresh air in bin zone 3, as I mentioned earlier, is greatly increased over the minimum ASHRAE requirement of 15 CFM of outdoor air per person. And why is this important? Well, a gentleman by the name of Bill Fisk at Lawrence Berkeley Labs has done a lot of work and has shown very convincingly that worker and student productivity increase as outdoor air increases above the 15 CFM per person level. One other studies have shown that short-term sick leave actually goes down. In summary, not long ago, VAV and IAQ were two mutually exclusive acronyms. I guess the question is, if we have a VAV design that can reduce refrigeration costs, reduce humidification costs, reduce fan energy costs, reduce the spread of airborne pathogens while increasing worker and student productivity and reducing short-term sick leave, why not use it? Thank you.
Thanks, Mike. So I'll be talking now for the rest of the presentation here. So I'll be going over low energy and high hygiene products. So I'll start off by touching on the ASHRAE 170 standard, Nortec's commitment to hygienic humidity solutions, and then finally finishing with the Nortec DL. So here's a Nortec's entire product range. As you see, we have it split up into two different sections. One side being steam generation, so your classic humidifier products with electric or gas or using building steam as your mode of energy to boil water and produce steam. The other side of this is using an atomizing or evaporative adiabatic technology. And the adiabatic technology that Mike was speaking about would be a media type humidifier. So this would be a wetted media that the air passes through and absorbs moisture from there into the airstream. And that is the ME series shown at the bottom. What I'd like to talk about, though, is the DL series, as the ME series is not yet recognized by ASHRAE to be used in hospital environments. So the ASHRAE 170 standard requires either a steam humidifier or an adiabatic high pressure water atomizing humidifier, which the ME or a media type humidifier does not qualify as. This would either have to be high pressure atomizing nozzles or something like our DL system. So the water has to be treated with reverse osmosis process. A UVC sterilization light needs to be used and a submicron filter as well. So there is quite a bit of hygienic rules that are incorporated in this standard, and I'll talk about how the DL meets all of these standards as well. But first, so what does water hygiene mean? So the aim is to limit the number of microorganism growth and bacteria and biofilm, both in water and in the HVAC system entirely. So germs are the microorganisms, they're bacteria, they're viruses. Viruses are particles or proteins of nucleic acid that can attack human cells and can cause disease. So we're trying to limit the number of viruses and the number of bacteria here by treating our water. And Nortec's been doing this for a number of years, and we've become experts in this field. So we're the water experts, and we do this in 3 steps. 1, by offering pre-treatment RO water skids. 2, by treating excuse me, our water throughout our system, and I'll be covering how the DL does this. And 3, by checking the hygiene and sanitation of our installations. So as I mentioned, we have the isothermal steam, so this is clean steam. So there's very limited amount of hygienic worry with those systems, and they're always used classically in healthcare systems. The next would be an adiabatic system, so using UV light, such as the DL does, as well as silver ions and auto flushing. And then we have our service department, so we can use back to quant testing to test the water that is available on site and see if it meets the standards for our equipment. So the Nortec DL is comprised of two different systems. So we have an atomizing nozzle on one side, a low pressure atomizing nozzle that has either 3, 7, 15, or 31 stages of control, so for pure modulation as you go through there. The second set is an unevaporated, all the unevaporated water from those nozzles land on a section of ceramic media, and the rest of that water that is suspended then by that evaporative media is picked up by the air as it passes through and brought into the airstream to reach the required humidification level. Here's a diagram of the entire system. So as you can see, what's provided by Nortec, we have the softener and RO as optional items from Nortec. The RO is required for the system. And then with the system itself, with the DL, we have the DL controller, we have the hydraulic unit, and the nozzle grid and post evaporator, so the ceramic media itself there. So to go through the system a little bit more, it is a complete bespoke system. So it's completely customized to your air handler or duct. It can have up to 31 stages of control, which provides a ±2 control accuracy. It can be from 5 all the way to 2,200 pounds per hour of spray. Very low pressure drop throughout the entire system. And to meet the ASHRAE standard, it has the silver ion patented hygiene system, which adds silver ions into the RO water to both keep the nozzles of the DL hygienic, but also continuously sprays the ceramic media with silver ions, eliminating any sort of bacteria growth on them as well. The entire system is very low maintenance and has a life expectancy of more than 15 years. The ceramic media has a lifetime usage on there. There's no need for cleaning. Throughout its lifetime, they will start to become silver from those silver ions, but in no way does it affect the performance of the unit. It also has quite a small footprint. The installation length can go as short as 24 inches between the nozzles and the ceramic media. It gives that guaranteed absorption distance, whereas with a conventional high pressure nozzle system, that absorption distance can become much longer than 24 inches. So for how large the system can get, the width minimum is 18 inches of the duct, but it can go all the way up to 165, and even with custom widths up to 330 inches. For height, we start at 18 inches and can go all the way up to 157. And the increments are about 2 inches in increment each time. The capacity can go all the way up to 2,200 pounds per hour, as I mentioned before. So taking a closer look at these ceramic tiles, they're a patented hygienic ceramic material that ensures an aerosol-free air outlet. The pressure drop across them is about 0.2 inches of water column at 500 feet per minute. Because of how porous they are, they have a great evaporation efficiency with a large surface area. And as I mentioned before, there's no need for replacement of these throughout the lifetime of the product. Additionally, we have an optional droplet separator that's also available. We recommend this for any air velocities over 600 feet per minute, and this would be installed downstream from the ceramic media. On the nozzle side, these are classified as low pressure nozzles. This allows for low wear and tear on the nozzles themselves, which gives both low maintenance and low replacement quantities needed. For the skid pump itself, we have two different types. So we have type A, which has 3, 7, 15, or 31 stage control with a VFD pump, and type B, which is the same but without the VFD pump. The VFD pump simply once turned on, gives you a completely linear modulation throughout the system. So it improves that modulation when it's above 60 to 70% of the unit capacity. So the unit does have precise control accuracy. The system runs through its 15 output levels, or 31 stages of spray circuits. Only afterwards the speed-controlled pump works, and the highest possible control accuracy is achieved. So, as I mentioned on that last slide, once it gets above that 60 to 70%, that VFD pump can turn on and give you complete modulation control. This is the only adiabatic humidifier on the market with the Fresenius hygiene certificate. This was done by a third party. It certifies that the humidified water is extremely hygienic throughout, and that the silver concentration in the drain water is below that minimum requirement. So for our testing services, this is what we've determined, and it does meet this certification that's being done by the European standards, so our Condair parent company. For North American installations, for hospitals and laboratories, we've installed it in the Parkland Logistical Clinical Lab in Dallas, the Memorial Sloan Kettering Cancer Center in New York City, and St. Jude's Hospital as well. We've also had installations for electronic and chip factory, such as Texas Instruments plant in Dallas, Texas, and a total of 23 DL units by the end of the project for that one. So they have completely switched over to this project. Thank you guys for joining us for the webinar. Feel free to contact any of our speakers, and I'd like to open up the floor to any questions. So we'll leave the question period open for the next 5 to 8 minutes or so. Feel free to type it in the GoToWebinar application, and we'll read them out as they come in, and myself, Stephanie, or Mike will be able to answer it.
I see 3 questions on the poll.
Sorry, Stephanie. Oh.
I see 3 questions on the control panel.
Okay. Yep,
4.
I see them here. Yeah. Okay, so Steve is asking, what is the percent of outside air considered for your VAV model? So Mike, that one would be directed at you, I believe.
Okay. It's 100% outside air at all VAV flow delivery to the building. And the minimum would be established by ASHRAE Standard 62 or local codes.
Okay. Nagesh is asking, what is the current trend of humidifying office spaces?
Is that for me, Graham, or?
If you'd like to touch on or start touching on it, that'd be great, Stephanie.
So that's a great question. At the moment, even though the research is coming out fairly rapidly around the benefits of humidification in office buildings, to my knowledge, most of the time, humidifiers are not actively implemented for worker health or productivity. I recently had a conversation with somebody who works for the IT part of the Department of Defense, and he told me that the Department of Defense computer workers realize how beneficial indoor humidity 40 to 60 is, so they actually pay out of their own salaries $10 a month to keep their offices humidified. So that, they're the early adopters, such as that, and the GSA, the General Services Administration, has now almost finished a big study looking at the benefits of humidification. But to answer your question, the short answer is it's really not done very much for human beings.
And of course, we're trying to change that through these presentations and our ASHRAE involvement.
And anyone listening, the more data we can get around indoor humidity levels or indoor air hydration levels, and absenteeism or influenza rates, cold, sinus infections, asthma, kids missing school, collect as much data as you can and send it our way, because we would really appreciate that.
Okay, that seems to be all the questions we have for now. If any of you would like to follow up with questions or contact us, the contact information will be made available, as well as the rest of this presentation, so an entire recording of it as well. Okay, with that, I think we'll turn off for the day, and I'd like to thank everyone for attending. Thank you.
Thank you very much.